everyone. I'm going to be talking about Ethereum pre-confirmations. I only have 15 minutes, so I'll get started as quickly as possible. So the presentation will have two parts. First, I'll talk about decentralized pre-confirmations, and then a specific type of decentralized pre-confirmations called base pre-confirmations. But before talking about decentralized pre-confirmation, I guess we should just recap real quick the centralized pre-confirmations. So the way they work is that we have a user at the top here, and we have what we call a pre-confer that gives the pre-confirmations. That's the sequencer for a rollup. And it's very simple. The user just makes a request to the pre-confer, and the pre-confer responds with a promise for pre-confirmation. And that's a promise, for example, that your Uniswap trade will execute at a certain price, at a certain position within the block. So these are pre-confirmations on execution. Now, when we move to decentralized pre-confirmations, there's a little bit that changes, which is the sequencer or the pre-confer changes at every slot. So here we have this notion of a look ahead, so we can see in the future who will be the next few sequencers or pre-confers, and they change at every slot. And so what the user needs to do is they need to be careful to talk to the right pre-confer, specifically the one in their current slot. And it's the same flow. They make a request and they get a promise as a response. And another important detail is that because you're in a decentralized setting and you can't trust any of these sequencers with reputation, you have to use stake. So you have to be staked or restaked. Hence the topic of this talk and this event. Now, because we have stake, we're in a position to punish financially these actors. So if we have a pre-confirmation promise plus an unhappy user, meaning that the pre-confirmation was reneged, it did not happen, then there's going to be slashing. Now, there's two types of unhappy users. There's two types of faults. There's what we call a safety fault, which is where the pre-confer made a promise, but they included on-chain something completely different, something that is inconsistent with what they promised. And then there's this more subtle fault, which we call a liveness fault, which is when the pre-confer made a promise, and then when it was their time to build a block, a few hundreds of milliseconds later, they just went offline. So there's something that shouldn't happen very often, but it can theoretically happen. And in both of these cases, basically, we want to financially penalize the pre-confer for not honoring the pre-confirmation, and this is where stake and slashing comes in. Now, one of the things that we do need to change is how block building works. So, what in a decentralized setting for a decentralized sequencer, I expect PBS to be the dominant way that blocks are built. And the way that PBS works is that you basically have builders talk to relays, talk to proposers. And it's a unidirectional flow of information where the blocks travel from the builders to the proposer. But when we have pre-confirmations, we're basically giving the proposer or the pre-confer or the sequencer, this same entity has multiple names because they're effectively doing multiple actions. There's this one entity that has monopoly power to build a block, and so they can do all these things. They have made pre-confirmations with users, and so you see these pre-confirmations need to go upstream and basically restrict how the builders are going to build their blocks. So if, for example, the pre-confer told the user, I promise to include your transaction at the very top of my block, well, the pre-confer needs to go communicate that to the builders through the relays. And then at the end of the slot, when it's time to actually build the final block, well, the builders need to respect this constraint that the very first transaction is as promised to the user. Now, if we were to just very briefly compare and contrast decentralized sequencing and centralized sequencing, it's actually fairly similar, but there's just a few key differences. One is that the sequencer, also known as the pre-confer, in a centralized setting is fixed, right? That every single slot is the same entity. So, for example, With Optimism, it might be the Optimism Labs sequencer, or with Arbitrum, it might be the Opchain Labs sequencer at every single slot. Whereas in a decentralized setting, we have this rotation going on. That's almost the definition of being decentralized. The slashing works also differently. So today, the status quo for centralized preconfirmations is this idea of reputational slashing. I, as Optimism labs or off-chain labs, I have billions of dollars of reputation. It is not to my advantage to renege these preconfirmations. People will go on Twitter and complain if I don't honor my preconfirmations. And on the other hand, in a decentralized setting, we just use stake. And then there's also another thing which is slightly different, which is that in a centralized setting, it's very easy to deal with MEV in a policy-based way. And this is due to the fact that you have a reputation. So, for example, the centralized sequencers can make a promise that I'm going to include transactions in a first come, first serve way. And I promise that I'm never going to sandwich you. I'm never going to front run you. And so today, as a service, these pre-confers provide MEV protection and they don't extract MEV. But in a decentralized setting, you can't trust the pre-confers, and so it's more of a market-based approach with PBS. And so if you want MEV protection, then you need more fancy tools like encrypted mempools. Okay, so now on to part 2, which is I guess the point of this talk around based preconfirmations or Ethereum preconfirmations. What does based mean? It means that is the layer 1 Ethereum itself that is doing the preconfirmations, the L1 proposals. So why do we even want to use Ethereum L1 to do the sequencing and the preconfirmations? Well, it has to do for the exact same reasons that we want to use Ethereum for settlement and data availability. So people today realize that Ethereum has this great properties for settlement and data availability, but sequencing is kind of this new unlock. And here are the reasons that I was mentioning. One is that you inherit the security of L1. You also inherit the credible neutrality of L1 once you use these Ethereum modules. And then 3, you also inherit from the network effects of the layer 1. So for the network effects specifically, today we're in a position where every Rollup is its own silo from the point of view of synchronous composability. And if we were to all opt into this notion of a shared sequencer, and specifically if we were to use the L1 chain as the shared sequencer, then we'd be in a position where we maximize the amount of network effects through synchronous composability. Okay. And by the way, credible neutrality is also extremely important in the context of a shared sequencer, because there's a coordination game. So for example, Optimism, if they were to create their own shared sequencer, would Arbitrum use it? Probably not. And vice versa. If Arbitrum were to create a shared sequencer, would Optimism use it? So we really need some sort of credibly neutral platform that everyone feels comfortable opting in. And we also obviously want extremely high security. Because if we have a new shared sequencer with a new token that can be 51% attacked, well, now there's a new attack vector, and your liveness to an extent degrades to the economic security of this new token. Okay, so how do we get the L1 to provide preconfirmations? Well, one of the things that we need, remember, is this notion of restake. So we need some subset of the L1 proposers to opt in to becoming shared sequencers, to becoming sequencers. And so it can't be all of the L1 proposers. It has to be a subset. So the ones in green are those that have put forward some stake. And the one in gray are the ones that didn't put forward stake. And we're going to give them a different name. We're going to call them includers. So this is the beacon chain look ahead. It's at least 32 slots, slot n up to slot n plus 31. And so one of the things that we need actually is sufficiently many of the validators to opt into this mechanism. We need about 20%. So once we have 20% of validators that have opted in, with very high probability, there's going to be at least one sequencer in the look ahead. Now, what the user will do is, just like in the previous slide, they will send a preconfirmation request to the very first sequencer, or also known as preconfirm, and then they will get a promise from that entity. And what the rollups will do in the context of base sequencing is that they will give the sequencing rights to these entities in green. So basically, one way to think about it is that as a base rollup with preconfirmations, I basically have these weird slot times. So for example, here, this slot would be made out of 2 Ethereum slots. So it would be a 24-second slot. And then if all of these are gray except this green one, then the slot from the point of view of the sequencer would be made of these 30 slots. Okay, so we have, these are the sequencers, and the preconfirmations work just the same. But there is a small optimization here, which is that we can use these includers to accelerate inclusion and settlement of pre-confirmed transactions. So if the pre-confer has already committed to including, this batch of 100 transactions, at the top of the block for these rollups, well, in some sense, it's been, quote, finalized. The ordering has been fixed. And so that batch of transactions can be communicated to the proposer as well n, and that can be immediately included and executed. And so you see, we're in a context where we get optimal pre-confirmation latency, on the order of 100 milliseconds, because you're dealing with internet speeds with a centralized entity here, and you also get next lot inclusion and settlement of your transactions by default. And there's an incentive to include these transactions just through the normal tip mechanism. So the preconfer can create a rollup block as an L1 transaction, include a tip, and that most of the time will get included in the next slot. Okay, great. And then again, same thing here. We're in the position where the proposer needs to communicate through the relays these constraints on the block builders. But there is a problem here with this image, which is that the proposers are meant to be running on Raspberry Pis with a home internet connection, right? The L1 proposers are meant to be extremely small nodes that are unsophisticated. And here we're basically asking them to talk to the users and pre-confirm transactions for all the rollups. So they need to be running full nodes for all the rollups. They need to have extremely high bandwidth and extremely high uptime. And this doesn't work too well. And so there is one idea which is really cool called execution tickets, where the notion of being a proposer, an L1 proposer, is now offloaded to the market and is not given to the validators. And so as a validator, I'm mainly doing just attestations, which is super simple, and I'm no longer a proposer. But unfortunately, execution tickets will take a few years. So we need another intermediate solution, which is this notion of what I call a gateway. So the proposer can delegate their rights to being a preconfer to a gateway, and it will be the gateway that does the actual heavy lifting of talking to all the users and having a very high uptime and running full nodes for all the different base rollups. Okay. Now I kind of want to give you an update on which rollups have decided to become base rollups with preconfirmation. So initially it was mostly Tyco that was going in that direction. But now Coinbase is also going in that direction with their key value rollup. So they're building a rollup which is separate to base, that basically is like a simple key value store, and they're building it as a base rollup. And then there's another rollup called Rise, which is not super well known, which has also committed to becoming a base rollup. And then there's this other group of rollups which are, or projects that are considering becoming a base rollups. And, for example, Aztec, I'd say there's an 80% chance, based on the discussions that they're having, that they will eventually become a base rollup. And there's also one of the very top rollups in production today that, based on the discussions that I've had with the team, is very, very likely going to be a base rollup. And then you have interesting projects like ENS, where one of their main constraints is credible neutrality, right? They want to enjoy the low fees of being on an L2, but they can't specifically pick an ecosystem. They can't pick the Polygon ecosystem or the Arbitrum ecosystem or the Optimism ecosystem, because that would be choosing sides, and they want to remain credibly neutral. And so for them, like, probably the best option, and based on discussions that I've had with them, is to actually deploy as a base rollup so that you can simultaneously retain the credible neutrality of Ethereum and the low fees of being on an L2. And then there's a whole ecosystem of teams that are actually building this. So it's quite a recent idea. It's only a few months old, but there's already, especially these teams here at the bottom in green, that are actively putting resources to write the specs and the APIs and write code. So this is something that is moving super quickly. And I think I might be out of time. If not, I'm happy to take questions. Thank you so much.